Hello, class. So today I want to cover just the first page of 10.3. This is the last section we need to know for the upcoming test this Monday, April 13th. And again, it's a 90-minute test. You should take it in one sitting, and you pretty much have all day to decide which window of 90 minutes you want. Yeah, so just try to do it in one sitting so that way you get to maximize your time. Should be about 10 questions, one question per section. So it starts at 8.4 and it ends at 10.3. So from 8.4, all the sections we've done till 10.3. It's a total of 10 sections. So supposedly the test will be one question from each section. And as of now, you get one attempt for each question. That might change to 2 attempts. I don't know yet. It's not up to me. So, there's a chance. I'll let you know if I find out. If not, then try again and see if it works. Okay, so let me just do the first page of 10.3, which is normal distribution. So I'm looking at my notes as I'm reading along. I'm outside of my backyard. I don't know, it's a little sunny probably, so hopefully it doesn't hurt your eyes. Okay, so anyway, it's a nice cloudy day here, blue sky with some nice clouds in there. So 10.3, normal distributions. This is the most helpful, important, widely used continuous probability distribution function in statistics. So it is another PDF. It's another type of probability density function or probability distribution function. Either way is fine, which means the area under the curve is 1, which means we get to ask probability questions because probability is based out of 1. So the first example I have in the notes is heights of people. So heights of people is actually a normal distribution. Most people are about around the mean, the average. And then, of course, you got your outliers that will be in the tails of this bell-shaped curve because these normal distributions have graphs that are bell-shaped curves. And the area is going to be 1 because it is a PDF. And normally in the sections before, we would integrate to find areas in the subintervals of this probability density function. And the areas would correspond to probabilities because, again, the area is out of 1. But this section is unusual because it turns out the function that gives these bell-shaped curves is not integrable. You cannot integrate. So not every function is integrable. So we have to use tables because these integrals can be approximated by numerical methods. So it's easier just to use the tables for this section alone to find probabilities or areas. Same idea. Remember, integrals give us area or probabilities when it's a PDF, but this section is very unusual. These PDFs, the bell-shaped curves, are not integrable. So we must use tables to find the areas and or probabilities. Same thing. Okay. So, like maybe the average height for an adult is, say, 5'7". So that would be our mean, or mu. And maybe the standard deviation is 2 inches. So one standard deviation above the mean would be 5'9", because 5'7" was the mean. One standard deviation below the mean would be 5'5". And then a property of these bell-shaped curves is if you're within one standard deviation of the mean, that covers 68% of people in a normal distribution will be within one standard deviation of the mean, plus or minus. So if the average is really 5'7", and we'll say the standard deviation sigma is 2 inches, then 68% of the population will be anywhere from 5'5" to 5'9". That's a theorem. Okay, so let's see. So the probability function, which you do not have to memorize, is f of x equals, here's the model, it's e to the negative 1/2 times x minus mu over sigma squared all over sigma times the square root of 2 pi. Again, sigma is the standard deviation and mu is the mean. And it's really just a transformation of e to the x squared, which is not integrable. Okay, so how do we find probabilities? We use the table. I think it's table C or table A. I gave you a copy of this table in Learn. or you can just go to your book. I think it's Appendix C if you want to see it. All right, so my first example on the bottom of this page of 10.3, which is also in Learn, talks about the weight of adult domestic cats. Meow. Are naturally distributed. So the weights of adult domestic cats are normally distributed, i.e. they follow a normal distribution. And let's just say that the mean weight is mu equals 7, and let's say the standard deviation sigma is equal to 2. Then what you can do is draw a bell-shaped curve, because it looks like a bell, and in the center of that bell-shaped curve is mu, which is 7. Let me see if I can show you the notes here where I'm looking at. So I'm looking at the bottom. Anyway, hopefully you can look at these notes as well as you hear me along. So there's the bell-shaped curve on the bottom. Mu is equal to 7. And then you draw 3 tick marks. Draw 3 tick marks to the right of mu, where the first tick mark is going to be 1 standard deviation above the mean if you go to the right. So that's why the weights are 7, and then 9, and then 11. And then when you reach 3 standard deviations above the mean, we're at 13 pounds. 13 is, that's pretty big for a cat. So that's in the tail of the curve. And then likewise, if your cat is underweight, you go to the left of the mean. And if you're only 1 standard deviation below the mean, then the cat is going to be 5 pounds. If you're 2 standard deviations below the mean, the cat will be 3 pounds. If you're 3 standard deviations below the mean, the cat will be 1 pound. And now here's something amazing. For all of these bell-shaped curves, 99.7% of all cats will be somewhere between 1 pound and 13 pounds. So in other words, if you're going to be 3 standard deviations away from the mean, plus or minus, then 99.7% of the population will be in that zone. Okay, so this model, because it's a bell-shaped curve, it never hits the x-axis. So the domain is actually negative infinity to infinity, which means it actually allows for a 100-pound cat, even though theoretically that's impossible, or a negative 50-pound cat, whatever the case may be. Okay, so almost all cats, like I said, will weigh within 3 standard deviations of the mean. In other words, between 1 and 13 pounds. Okay, let's go to the flip side of page 1. And it says, select 1 cat at random. Sketch the area corresponding to what is the probability that the cat weighs between 9 and 11 pounds. So symbolically, here's my dog. Let me show you my dog here. Okay, select 1 cat at random and sketch the area corresponding to what is the probability that the cat weighs between 9 and 11 pounds. And here's the picture of that. It's always good to draw a picture of what's being asked. Just a rough sketch, and here it is. Okay, sorry, this is probably not the best video, the way I'm showing the notes and everything. Okay, so you shade the area between 9 and 11, and you can see it's a small area. So I know the probability would be way less than 50% to get a cat between 9 and 11 pounds. Then I ask, shade the area for probability x greater than 13, and also x less than 13. So to be greater than 13 pounds, that would be very, very unusual. You're talking about 3 standard deviations above the mean. So it's hard for me to show it well. Oh well, okay. But obviously, so that's a small area, which means it's a small probability, because area is probability since it's a PDF. But the other question, the probability that any randomly selected cat will be less than 13 pounds, that's a large probability. It's practically the whole curve underneath. Okay, so next, we should draw sketches before actually finding the probabilities using the table, so that way we get a ballpark figure. So what's the probability that our random variable x is less than 7, meaning that the cat will weigh less than 7 pounds, and that's half the area. So without even looking at the table, we know it's going to be 0.5000. The table gives the probabilities to 4 places. And likewise, what's the probability that x is greater than 7? It's also going to be 0.5000, 50%. So the probabilities are taken to 4 places on the table. Okay, and then finally, to conclude this, because we're going on 10 minutes already, the most important distribution, the standard normal distribution, it has mu equals 0, which is the mean, and sigma, the standard deviation, is equal to 1. So symbolically, we write a capital N parentheses 0, comma 1. And then here's my last statement. We can take a normal distribution and convert it to the standard normal distribution. Why do we standardize? Because it makes life easier, because we only need one table, the standard normal distribution table, rather than doing calculations individually for each value of the mean and standard deviation. Done!